So let's recap where we've got to so far. Particles have both wave-like properties and particle-like properties, and a useful way of encapsulating all that information is to think of the particle as a wave packet. So a little wave which is of some finite duration in time, so it's restricted in space, but clearly has that wavelength associated with it. The other thing that we've seen is that there is a sort of a way to construct these wave packets, which involves adding a whole bunch of sine waves together. And there is this fundamental relationship that comes out of Fourier analysis, this technique of creating waveforms by adding sine waves and cosine waves together, which is that the shorter you want the duration of this pulse to be, the larger the range of frequencies that you have to add together in order to get it. And we can put that in more mathematical terms. It's really rather a simple formula that says basically that the range of frequencies that you have to add together multiplied by the duration of the pulse in time is always of order unity. And as we've seen, if you want to create that, make that pulse shorter and shorter, so delta t gets smaller, you have to add a bigger and bigger range of frequencies together in order to get it to happen. This is a very fundamental result, and it actually has implications across a whole wide range of physics. For example, it means that a laser, although we're told it's usually thought of as a monochromatic source of light, never is truly monochromatic, in that because you've actually switched it on and switched it off at some point, that means that the wave is of finite duration. So delta t in this case can be very long, because you can leave your laser on for hours or months or years even, but it's still finite in duration, and that means that delta f has to be finite as well. There's a finite range of frequencies added together to create that very long pulse of light. At the other end of things, if you want to send information down a fiber optic cable, again, there's a fundamental limit here, because as you make the pulse shorter and shorter, because of course if you want to send more information down your cable, then you make your pulses really short, pack in the maximum amount of information. But as that duration gets shorter and shorter, delta t gets smaller and smaller, delta f, the range of frequencies that you have to add together to make that pulse, gets larger and larger, and eventually you end up adding such a wide range of frequencies together that some of those frequencies are so far along the electromagnetic spectrum that they won't propagate down the fiber optic cable at all, and so your pulse won't propagate properly along the fiber optic. But we're more interested here in dealing with particles and how this relates to these uncertainties in particles, and so that we can translate this delta f times delta t into things that we think of more typically in terms of particles. So delta f means there's a range of frequencies associated with that wave packet, which means there's a range of wavelengths associated with that wave packet, which from the de Broglie relation means there's a range of momenta associated with that packet. Or put another way, that means that our particle doesn't have a uniquely defined momentum. It has some uncertainty associated with what its momentum actually is. Similarly, because the pulse is finite in time, it takes a certain amount of time to go past us, that means it's spread out in space. That means that the particle's position is not uniquely defined either. There's a fundamental uncertainty in its position. And you can see we can trade these two things off against each other, because we can play with delta f and delta t, but the product of them is always going to be some finite number, which means that if we make the momentum, for example, very certain by using a very small range of frequencies, so that the momentum is very well defined, that means that the particle is going to be spread out a lot in time and in space, and vice versa. If we make it very small in space, so it's well defined in position, then its momentum is very uncertain. We can derive this result more mathematically. So from that fundamental Fourier property, delta f times delta t is of order unity, we can derive this thing called the Heisenberg uncertainty principle. So that's what I'll go on to do now, and I'll do it here on the whiteboard. Okay, so we have this relation that delta f times delta t is of order unity. And we want to change that, translate that into thinking in terms of these properties we're more used to dealing with the particle, so its momentum and its position. So the position one's quite easy, which is that the uncertainty in the position of a particle, so if a particle is traveling past us, if it takes a duration delta t, a time delta t to go past, and the particle's traveling at velocity v, then the two are just related by the simple formula that says that it's spread out by an amount delta x, which is equal to v times delta t. And because we want to think in terms of momenta, let's get rid of that velocity and write it as p over m times delta t, which we can rearrange just to say that delta t is m over p times delta x. Okay, so that's the position. Now we want the relationship between frequencies and momenta. So let's start with the fundamental properties of a wave, which says its frequency is equal to its speed divided by its wavelength. And again, we're going to get rid of the speed. We want to think in terms of momenta. So the speed is just p over m again. And the wavelength we can get rid of because we know the de Broglie formula that says that wavelength is related to the momentum of the particle by the de Broglie relationship. And so if we rearrange this, we end up with that frequency is p squared, and we end up with the h and the m in the denominator. So that's how a frequency is related to a momentum, but what we were actually interested in is if we have some small range of frequencies, what small range of momenta does that translate to? So to figure that out, we just have to differentiate this formula, which tells us that df by dp is equal to, so p squared differentiates to 2p over hm, which means we can write that a small range of frequencies, delta f, or a small change in frequencies, is approximately equal to 2p over hm times delta p. So now if we just go back to our original formula, delta f times delta t is of order unity, we can substitute in that delta f is 2p over hm times delta p, and delta t was m over p times delta x. Delta x is of order unity. And a few things will cancel from here. We can cancel p's in the numerator and the denominator, and m's in the numerator and the denominator. And we can rearrange this formula to say that delta p times delta x is of order. So we've got an h and a 2, which we take over the other side, h over 2. Now this is the fundamental limit, right? This is saying that you can never measure the position and the momentum of a particle to better than what this formula is telling us, but you can always do worse, right? You can make a bad measurement of a particle's position and get it wrong by more than this amount. So this is really only a lower limit, so we can always do worse. So there's usually a greater than sign in the middle there. The other thing is that you'll see different versions of this formula. Sometimes there's the factor of 2 there, sometimes it isn't, sometimes it's written with h bars instead of h's. It really is because it really is intended only ever to be a very approximate relationship, but it's telling you what that trade-off is between momentum and position, and this is the Heisenberg uncertainty principle. So there it is. That's starting from this wave packet picture of particles and this fundamental property of waves, that there's this trade-off between the duration of a pulse and the range of frequencies that you have to add together in order to produce it. We've been able to derive this fundamental relationship of the limits of this uncertainty in the position of a particle and its momentum, and how you can trade one off against the other, but you can never have both measured very accurately at the same time.